Hi everyone, this is Chen from PUC-Rio de Janeiro. So today I would like to share with you this recent work about the Spintronics in topological insulators, and especially emphasizing on the spintronic effects, how they are affected by the percolation of these topological edge states or surface states. And I will present both the 2D and 3D version of this problem. First, I would like to make a rather counterintuitive claim, namely that there's actually no equilibrium edge spin current in topological insulators. Now, this really surprising result that comes out of our calculation is actually because the edge state spin current is actually canceled out by the bulk bands. And as a result, the edge spin current occurs only at the finite chemical potential, by which I mean when the chemical potential is put away from the Dirac point. And also, when you make the topological insulator with a ferromagnetic metal together to make a bilayer, then we uncover that there will be what we call laminar currents occurring at the interface. And also, we will emphasize some of these topological spintronic effects. We will emphasize the percolation of the edge states, how the wave function can leak into the adjacent ferromagnet, and also how the ferromagnet can modify the spin momentum locking profile of these edge states. And also we have built a linear response theory, particularly for this subject of the current-induced spin torque. Now, first I should also acknowledge my collaborators. A lot of this work is done by my very outstanding student, Antonio Zegarra at PUC, and also a large collaboration is made with Carlos Egues in USP, St. Carlos. So first, regarding this issue of vanishing equilibrium edge current, this is best understood in the simplest topological insulator you can imagine, the 2D time reversal breaking Chern insulators. Now, you know these Chern insulators, they exhibit these counter-propagating edge states. And because of this, it's very natural to speculate that there will be an equilibrium edge current. And to really study this issue, we start from the following. We start from the continuous model of this 2D Chern insulator, the simplest version. We regularize it to the Hall-Brewing zone, by which I mean you replace this K by sine K, and you replace this mass M by the usual mass M plus a correction to a K squared term. And then you simply Fourier transform this into real space to build a square lattice model. And then you study the square lattice model in the strip geometry, that is a closed boundary condition in the X direction and open boundary condition in the Y direction. Now, as everybody knows, then in this situation that the edge state naturally occurs, where here the red shows the state whose wave function is more localized at the first edge, and green shows the wave function that is more localized at the other edge. And you see that they are counter-propagating, speculating an edge current. However, you see that these bulk bands, which are these quantized discrete bands, they also have this red, for instance, this one, they also have this a significant weight at the edge. Yeah? And moreover, you see that this red part of this edge current has a negative groove velocity compared to that of the edge state. So this means that the bulk bands are actually contributing an edge current that is against the current produced by the edge states. So to quantify this, we simply calculate the expectation value of the local current using this lattice eigenstates. And the result is this. If you count only these states inside these gap, in other words, if you only count these edge states, then indeed you see a current that is running on positive in one direction and at one edge and negative at the opposite edge, as you expected. However, if you include all the bands, including the bulk bands and the edge states, then you see that the current becomes zero everywhere. So this indicates that the current is really being canceled out by these bulk bands. And I should also emphasize that this result is very robust against tuning any parameters in this problem. In other words, tuning is hopping parameters, mass terms, or the width of this edge, the width of this strip, or temperature. Yeah. So all of which you see that this cancellation happens. However, the previous analysis indicates that implicitly, I assume that the chemical potential is at the Dirac point. Now, if you put the chemical potential a little bit below the Dirac point, then what you see is that now the cancellation is not going to be exact anymore, because this part of the edge state from the chemical potential until the Dirac point, this part you didn't count. Right? So the cancellation is not going to be exact, and therefore you're going to miss some edge current, so the edge current is negative. However, if you put a chemical potential above the Dirac point, then everything below the Dirac point is canceled out. But in addition to that, you have these additional edge states that contribute to the current, and therefore you are going to get a positive current. So as a result, the prediction is that if you sweep chemical potential through the Dirac point, you will actually change the edge current from negative to positive. So in other words, you can actually reverse the direction of the edge current by tuning chemical potential. Now, in addition to this sign changing with respect to the Dirac point, you also see this quantized stepwise features. Now, this is because we do simulation in a small cluster, so it is geometrically quantized. Now, so based on this, you can imagine the following experimental setup to measure this. For instance, you grow some kind of Chern insulated quantum dot on top of a big gate, and then you tune this voltage to change the chemical potential in this Chern quantum dot. Then you can reverse the edge current from clockwise to counterclockwise. And this way, the magnetic field that it produces can be changing from pointing up to pointing down. And this, in principle, could be measured. And the other way to control the chemical potential, for instance, it has also been shown experimentally that the chemical potential can be controlled by doping. Now, coming to the spintronic versions of this. In other words, I would like to discuss time reversal symmetric topological insulators. Now, for concreteness, I use this BHZ model as an example, which essentially can be considered as two copies of Chern insulators, one for spin up and the other one for spin down. And because of this, the edge current is no longer an edge charge current, but rather an edge spin current. And the spin current is the opposite of the two edges. Now we do exactly the same thing. We just take this BHZ model, which essentially is the continuous version, and then you regularize it to the whole Brillouin zone, and then you Fourier transform it to real space. And then once again, you do the simulation in the strip geometry that is continuous in X and open in the Y. And then you still see the same thing. You see that here the blue indicates the spin that is propagating at the first edge. Sorry, spin up that is propagating at the first edge. And green is the spin down that is propagating at the first edge. And you see that they are opposite in direction, indicating that there should be an equilibrium edge spin current. However, notice that in the bulk bands, you see you also have this blue components, and that has the negative slope of that of the edge state, indicating that indeed the bulk bands are producing an edge current that is countering the edge current of the edge states. And if you do this, you see that they still cancel out exactly if the chemical potential resides in the Dirac point. And if you sweep the chemical potential from negative to positive, then you can generate finite current, and then the finite spin current would reverse side as well. Now, given all this, the issue is whether this actually happens in real materials. Because notice that what I've been talking about here is that you take this low energy effective model and then you just extend it to the whole Brillouin zone. Now, if you compare this with the real band structures in let's say, the real 2D topological insulators, like this TMB materials, you see that the band structure has quite a lot of difference. And therefore, at this moment, we don't really know if this cancellation of the edge current by the bulk bands actually happens in this kind of realistic band structure. So more work needed to be done to clarify whether this actually happens in real materials. But the important message here is that the edge current is not entirely determined by the edge states alone. Yeah, the bulk bands can also contribute to edge current. Now coming to the 2D topological insulator and 2D ferromagnetic metal side junction. So as a first attempt to, let's say, to capture some features of these topological spintronic effects. So we study this kind of junction also in terms within the context of this lattice model. And we realized that the first thing that you should pay attention to is that, this 2D topological insulator materials, they are all semiconductor materials. When you put a semiconductor with a metal together, the first thing that you should worry about is the so-called Schottky-Mark rule. Namely, when you put these two materials to be in contact, what has to match at this interface is the work function of these two materials. And as a result, that the chemical potentials of both materials would have to shift a little bit in order to match the work function. So how it is shifted will depend on which materials that this junction is made. And therefore, we think that in general, you can have two kinds of generic band structures. The first is that you see that essentially you are just putting topological insulator bands with the ferromagnetic bands together. The first type of band structure is that you can have this, your edge state Dirac cones, let's say above this parabolic type of ferromagnetic bands. So in other words, the Dirac cone is totally outside of these ferromagnetic bands. We call this the pristine type of band structure. And the other type is that the shifting of the chemical potential is such that the Dirac cone is entirely submerged into the parabolic bands. And we call this the submerged type of band structures. Now, these two types of band structures, they heavily affect how the edge state is percolating into this ferromagnet. For instance, for the pristine type of band structure, if you track how the wave function of this edge state gradually merges into these ferromagnetic bands, then you see that close to the Dirac point, they have this very nice localized feature inside the topological insulator. But as you go gradually into the ferromagnetic bulk bands, then it just gradually merges with the quantum well state of the ferromagnet, because we have a very narrow ferromagnet, so it forms a standing wave inside. So this is more like this blue line here. While for the submerged type band structure, the feature is basically the same, but the merging is even more drastic. Basically, you cannot even tell, you cannot even distinguish whether this is more edge state-like or more ferromagnetic state-like. These states, they have both the feature of the quantum well state and also some tails localized inside the topological insulator. And moreover, if you look at the spin expectation values of this kind of junctions, you see that if the magnetization of the ferromagnet is not pointing along the direction of quantization of the topological insulator, then you see that the spin momentum locking of the edge state will be affected. So the spin momentum locking basically now will be pointing between the z direction and the direction of magnetization. And this feature is becoming more drastic in the submerged type of band structure as well. So, and also from these band structures, we see a very clear feature, namely in some directions of the magnetization, the band structure will become asymmetric between plus kx and minus kx. For instance, here is an example. You see that this plus kx part is not exactly the mirror symmetric of the minus kx part. So this asymmetry between plus and minus k motivates us to investigate this problem. Does this asymmetry mean that the whole Fermi C is carrying a finite velocity and hence it produces a persistent current? Now, to investigate this issue, it is also very easy. We just go ahead and calculate the current expectation value of this hetero structure. And this is the result for the charge current, that we see that indeed in this kind of hetero structures. So here I'm plotting the charge current as a function of the transverse coordinate y, where the dashed line separates the BHZ region and the ferromagnetic region. You see that indeed the system for both the pristine and submerged type of band structures, you will induce this kind of charge currents, which are positive in some y and negative in some y. So physically, it means that you produce the laminar current whose directional flow would depend on your transverse coordinate. And to put numerical precision, the total current sums to 0. So in other words, there's no net persistent current, but locally there's this kind of laminar flow that flows positive and negative depending on the distance away from the interface. And also, before I've shown you that the BHZ model itself has no edge spin current, but nevertheless, if you make it in conjunction with the ferromagnet, then we see that an edge spin current is induced. And also its sign is positive or negative will depend on the distance away from the interface. So intuitively, it looks like this. At the interface, near the interface, you will produce a persistent laminar current whose direction of flow is depending on the transverse coordinate. Now, coming to the issue of spin torque, we study this by using a linear response theory, where essentially we would like to study the spin polarization induced by external bias voltage or external electric field. So we calculate the spin induced by the electric field with this response function. We call it magnetoelectric susceptibility. And this you can calculate in the latest model version, and because you are calculating between the spin and the field, right? So it is a correlator between the spin and the current operators, and then multiplied by this function, which is essentially something like a derivative of the Fermi function, just in the usual linear response theory. And then once you calculate this, you can, once you have this susceptibility at specific value of bias voltage, then you can calculate what is the spin accumulation that has been produced. And then the spin torque will be just the spin accumulation inside the ferromagnet, cross product with the magnetization of the ferromagnet, according to the usual Landau-Lifshitz dynamics. So our result shows that indeed we have a profile of susceptibility, and we have a profile of susceptibility, and as a function of different interface couplings. These are different lines shown in the figure. Now you see that, first of all, at the free edge that is not making contact with the ferromagnet, we capture the so-called Edelstein effect. Namely, if you apply electric field to the TIs, then you will induce a charge spin accumulation. Yeah. And this is correctly captured. And on this side, this susceptibility that leaks into the ferromagnet is precisely what causes the spin torque. And also, we have investigated all the directions of these magnetoelectric susceptibility, and we conclude that the largest component is the one that is mainly along the direction of S cross Z. So if you would define the Z direction as your reference coordinate, then this will imply that your spin torque is mainly field-like along the direction of S cross Z. And also another interesting issue in this spin torque is a steep spin torque mainly contributed from the edge state or from the ferromagnetic states alone? And it turns out that if you do this linear response theory, first of all, you don't distinguish them. You just put them both into this, and then you see which kind of states contribute the most. And it turns out that both of these states are contributing. And moreover, you have the submerged kind of a situation that basically you cannot even distinguish the edge state and ferromagnetic states. So yeah, so this is, all of these are captured within our linear response theory. Now coming to the experiments, now it seems like pretty encouraging that these experiments using 2D, mainly these TMD materials, in hybrid with this ferromagnets, they indeed reveal mostly the field-like kind of torque. However, I should emphasize that experimentally, how they define the field-like or damping line is with respect to the y-axis. Now, this is because of some the usual spin Hall effect, spin orbit torque kind of system, right? But our message to experimentalists is that the spin torque in this kind of system is better defined with respect to the z-axis. Yeah. So we're hoping the experimentalist can redo this kind of analysis, but with respect to the z-axis. Now I'm done with 2D. Now, so I'm going to start talking about 3D. So 3D, let me just go through this real quick, because the issue is also, firstly, do we have a equilibrium surface spin current or not? So it turns out that you use the same procedure to build a lattice model to study the edge currents. Then you still see that the bulk bands always contribute to a negative current that tries to cancel out the edge state spin current. And at the end, there's no equilibrium spin current if your chemical potential is reside at the Dirac point. And there is finite current only if your chemical potential is finite. And moreover, the current switches direction between positive bias voltage and the negative, positive gate voltage and negative gate voltage. And also, if you make ferromagnetic thin film deposit on top of these 3D TIs, so it looks more like this kind of layer, atomic layer structures, then you will also have this dichotomy of the pristine type of band structure, where the Dirac cone is mainly outside of these parabolic ferromagnetic ball bands, or it could submerge deep into these ferromagnetic ball bands. And these two have very different effects on the on the profile of the wave function of the edge state. You see that once again, for this submerged type, you see a more dramatic leakage and merging with the ferromagnetic quantum well states. And also, once again, we see that the band structure is asymmetric in the direction that's perpendicular to the magnetization. Then we investigate whether this will produce a laminar current and laminar spin current. So it turns out that indeed it does. So either for pristine or submerged type of band structure, you see once again that is persistent currents whose direction of flow depends on your outer plane coordinate. Yeah. And also 3D TI alone does not have a surface spin current, but once you make it in conjunction with the ferromagnet, you started to induce a laminar spin current near the edge. So the physical picture is that now is that this the directional flow of these persistent currents will depend on the layers, which layers you are with respect to the interface. And we have also applied the same linear response theory to study the spin torque in these materials. And what we have found is the following. So here we emphasize particularly the effect of the impurities. So the upper left figures are in the weak impurities, and the lower left, the upper two figures are in the weak impurities, and the lower two figures are the strong impurities. And the first feature you see that is that the Edelstein effect at the free edge of the topological insulator is dramatically suppressed by the impurities. Now, this is consistent with the semi-classical calculation in terms of the Boltzmann transport equation. And also the spin torque. So once again, you have finite susceptibility, finite magnetoelectric susceptibility inside the ferromagnet, and this is what causes the spin torque. And once again, the spin torque is found to be mainly field-like, and also both edge state and the ferromagnetic states will contribute to this torque. Now, coming to the experiments, there have been a number of very famous experiments performing using this 3D topological insulated materials and the ferromagnetic metal, this kind of hetero structures. What they found is a large damping-like feature. Yeah. So from our analysis, we see this is largely field-like. So this we conclude that the large damping-like torque that is seen experimentally is likely due to other kinds of mechanisms that we did not take into account. For instance, there have been a lot of theoretical works that proposing other mechanisms that possibly can introduce this kind of damping-like torque. But what I mean to emphasize is that if you take into account only the contribution, the percolation of the edge states without all these other complications, then the torque will be only the field line. Okay, here comes to the end of my talk. And in summary, in the talk today, I have first shown you that there's no equilibrium edge spin current in these topological insulators because of the cancellation by the bulk bands. And the edge current only occurs at a finite chemical potential, and moreover, it can be switched to different direction by the chemical potential. And this topological spintronic effects is largely affected by the percolation of the edge states. And this is also further highly affected by the type of band structure, whether the band structure of the TI is has a large overlap with the band structure of the ferromagnet. And also we calculated this non-equilibrium current-induced spin torque, which turns out to be largely field-like. And with that, I would like to thank you for your attention. And if you have any further questions, don't hesitate to contact me. Thank you very much.